Are you ready for the last notes for the year? Woohoo! Here we go. Your favorite word problems. Let's talk about some applications of rational equations. For this section, I'm going to go through each problem, help you set up the equation. I may solve a few of them with you, but the others I'm going to have you solve on your own. Okay, so let's look at the first scenario, and that is a work problem. So when we talk about work, we use W to represent work. And it says that work is represented by the amount of work is accomplished when R is our rate and T is our time. So work equals rate times time, right? So how fast we go times how long we're working tells us how much has gotten completed. Now, if a job is complete, we say that the work equals 1. It's 100% completed, so that equals 1. Our rate is always 1 over the time it takes someone to complete a job fully. Okay, so let's look at this first example. We have Helena and Kareem are working on a neighborhood cleanup. Kareem can clean up the trash in the area in 7 hours, while Helena can do the job in 5 hours. How long will it take them if they work together? The confusing part is that it looks like we have times talked about everywhere, right? 7 hours seems like a time, 5 hours seems like a time, and then they're asking us for time. Well, the 7 and the 5 actually help us to find the rate. So we can set these problems up in a variety of ways, but I'm going to just sort of organize it based upon each person. So for Helena, we know her rate is going to be 1/5. And the reason for that is because she can do the job alone in 5 hours. So that means in 1 hour, she gets 1/5 of the job complete. Now, how long she's working for, we don't know. She's not actually working for 5 hours today because that's when she does it alone. She's working with Kareem. So we don't know her time. Now, we have Kareem. Kareem, his rate, he can do the job alone in 7 hours. So that means his rate is 1/7. He gets 1/7 of it done in 1 hour. Now, the time he's working for today, again, we don't know. He's not working alone, he's working together. Now, Helena and Kareem are working together on this. So if Helena's time is X, means Kareem's time is X. Now, what does that mean? We want to actually put their work together to get the job done. So I'm going to first represent Helena's work. Work is rate times time. So Helena is her rate times time. This expression represents the amount of work Helena will get done. Now they're working together, so I'm going to add Kareem's work. His is his rate times time. Together, these two amounts of work that they get done is getting the job complete, so it has to equal 1. And so now we go ahead and we solve this. This would become x over 5 plus x over 7 equals 1. We don't have to worry about our domain because there's no variables in the denominator. And so now to solve this, like we've done, we find the LCD and multiply by through. So that LCD is 35. This would give me 7x plus 5x equals, don't forget to distribute it all the way to the end, equals 35. Now we combine our like terms and solve for x. So when I divide, we get that x equals 35 over 12. And if you want to approximate that, you can. So we get x is approximately 2.9 hours. It will take the two of them about 2.9 hours to get the job done. Okay, so notice here, we're using, for our word problems, we're still using sort of that 5-step situation. Step 1 is to organize your work. Step 2 is to define your variables. We did that where we said our time is x. Step 3 is to write our equation. Step 4 is to show our work. And then 5 is to write a sentence or make sure your answer is with a label. So 2.9 hours. Okay? Let's do number 2 together. We're going to set that up, and then I'm going to let you solve it. So this is another work problem, and it says at a factory, smokestack A pollutes the air twice as fast as smokestack B. When the stacks operate together, they yield a certain amount of pollution in 15 hours. Find the time it would take each to yield that amount of pollution operating alone. So this time around, we have the time. Okay, so if we organize this again, similarly to how I did above, we have smokestack A and we have smokestack B. We want to know smokestack A's rate, its time. We want to know smokestack B's rate and its time. For this scenario, we have 15 hours. That's how long they're actually working for. So I'm going to put 15 for the time. What we don't know is the time it would take each on their own, aka what we don't know is their rates. I'm trying to avoid two variables. So I don't want to say our rate of 1 over x and 1 over y. We don't want to do that. What we want to do is get these both in terms of x. So what we need to remember here is that smokestack A pollutes the air twice as fast as smokestack B. Keep in mind what that really means. Who has a longer time, A or B? B does. So the rate of smokestack A is going to be 1 over x, where the rate of B is 1 over 2x. And that's a little tricky because it says A is twice as fast, so we'd think A should be 2x, but that means it's actually a smaller amount of time. So x represents, and we'll define that a little bit more specifically, x is the time it takes smokestack A alone. And therefore 2x is the time it takes smokestack B. So now we have the rates and their times, we can set up our equation, right? Together, they're both polluting, so they're working together. So therefore, the work that smokestack A is doing is its rate times its time plus smokestack B times its time, and that creates 1. Please keep in mind how when I'm multiplying by time, notice it's always going to go into the numerator because it's like 15 over 1. So now we have 15 over x plus 15 over 2x equals 1. Our domain here is that we can't have x be 0, but that wouldn't really make sense because that would be saying neither of them are working, and it's telling us that both are working. So now that I have my equation, I'm going to multiply through by that LCD, which is 2x. For the first one, the x's cancel, and I'm left with 2 times 15, which is 30. Then for the next one, everything cancels, and I have 15. And then lastly, we have 2x. So we have 45 equals 2x, which divided by 2 gives me 22.5 equals x. So what this is saying is that find the time it would take each to yield that same amount of pollution alone. It would mean that it would take smokestack A 22.5 hours, and smokestack B is twice as long, so that would be 45 hours. Okay, now those seem like big times, but remember, together it takes them still 15 hours. So on their own, it's going to be a much slower rate. Okay, so I did those ones together with you because those were both new ones with work. The next ones are types of problems we've seen before. Some distance, rate, time problems, some mixture problems, and so forth. So I'm going to just help you set them up, and then you will solve them. So recall for motion, we have distance equals rate times time, and setting up a chart is really helpful. So for number 3, a tour boat goes 10 miles against the current in a small river, in the same time it goes 15 miles with the current. If the speed of the current is 3 miles per hour, find the speed of the boat in still water. Okay, so that's what we're looking for. X is going to represent the speed of boat in still water. We're going to set up our chart. We will have distance equals rate times time. And our two scenarios are us going against and with the current. And we'll start to fill things in. So a tour boat goes 10 miles against the current. So 10 is our distance. In the same time, it goes 15 miles with the current. So 15 is our distance width. If the speed of the current is 3 miles per hour, okay, so remember, when I go against a current, my rate is going to get slowed down. So I take the speed of the boat and I get slowed down by the current. I subtract 3. When I go with, it's the speed of the boat plus the current. It speeds it up. Now, our goal is to not use two variables. So do I know how long? I don't know how long. So I don't want to put y in here. But what I know is that if I have two columns, I can always find the third. How do I get t alone? I divide by r. So I have d over r equals t. That means I can have 10 over x minus 3 in this box and 15 over x plus 3. Okay, what's my equation? Well, in the past, you may remember that we know distance equals rate times time, so we could literally just go across. But that's just going to cancel things. What we need to remember is that it's talking about same time. So my equation is going to be to set those two times equal to each other. And now you go ahead and solve. Okay, if we look at number 4, Maria jogs to the country at a rate of 10 miles per hour and she returns on the same route at 6 miles per hour. The total trip was 1 hour and 36 minutes. How long did her trip out take? Then find how far she jogged. So I'm going to help start the chart, but you have to finish it and finish coming up with the equation and solving. So we're going to do our same sort of thing here. Right? We have distance equals rate times time. And we jog to the country and then return, right? So we jog to the country at a rate of 10 miles per hour. She returns at 6 miles per hour. Makes some sense, right? Probably a little slower on your way back. The total trip took 1 hour and 36 minutes. How long did her trip take out? So if we know altogether her trip took 1 hour and 36 minutes, we have multiple ways to do this, okay? What's important to remember here, though, is that the 10 and the 6 are in terms of miles per hour. And 1 hour and 36 minutes is not just in terms of hours. So if you're going to keep 10 and 6, we need to convert 1 hour and 36 minutes to hours. So recall here, 1 hour and 36 minutes is the same thing as, right, how many minutes are in an hour is 60. So 36 over 60 gives me 0.6. So this is really saying 1.6 hours. Keep that in mind so that your calculations will all work out. So we can do this in a couple of ways now, okay? We have that if I know that altogether it took 1 hour and 36 minutes, we could say that time is 2 is x, and then return trip would be 1.6 minus x. Okay, and so we can define right there that x represents the time to the country. Now, what do I do for equations? Well, I can fill in that last box by distance equals rate times time, so this is 10x. And then this is 6 times 1.6 minus x. So I'm going to have you try to figure out what should my equation be to now go ahead and solve for x. Go ahead. Okay, 2 more. Number 5. A fraction has a value of 3/4. If the numerator is decreased by 10 and the denominator is increased by 20, the value of the fraction is 1/3. Find the original fraction. Okay, so if we have what we're trying to figure out is our numerator and our denominator. So it says a fraction has a value of 3/4. What that means is that my fraction could be 3/4, right? It could be 9/12, because if I reduce that, that gives me 3/4, right? It could be 30/40. That reduces to 3/4, and so on and so on. Lots of different options. So how did I find all those? Is that all of those were a multiple with 3/4. So what we need to understand is that that original fraction is something like 3x over 4x. No matter what x is going to be, that will reduce to 3/4. So I have a fraction that has a value of 3/4. If the numerator is decreased by 10, so if I subtract 10 from the numerator, and the denominator is increased by 20, now that fraction equals 1/3. Okay, so go ahead and solve that. And remember, our original fraction is 3x over 4x. So once you figure out what x is, you can plug it back in. Try solving that. Last but not least, a mixture problem. So Aaron adds 80% brine, which is salt and water, to 16 ounces of a solution that's 10% brine. How much of the solution should be added to create a solution that's 50%? So for our mixtures, I like to use a chart as well. Okay, we have really 3 different, I'll make this a little larger, 3 different things. We have the 2 solutions, right? So the first solution is a 80% solution. Our second solution is a 10% solution. And we're trying to create the mixture, which is a 50% solution. Okay, so we put our solutions first, or let's say we were making trail mix. Let's say we were talking about M&Ms and peanuts. Then you would have those first, and lastly, our mixture. Okay, the next thing you're going to have can vary. In this case, we're going to have the amounts. After that, we'll have our percents. And then this is going to represent the percent, the amount of pure brine. Okay, I'm going to leave that blank right now because that's going to differ. But our first column again will be our amounts. So Aaron adds 80% solution to 16 ounces. So we don't know the amount of 80%. So X represents the amount of 80% solution. I know I have 16 ounces of the 10%, and I don't know how much of the 50%, but since I'm mixing them, I know that this will be X plus 16. Our percents we can literally take, but we're going to write them as decimals. So 80% is 0.8, 10% is 0.1, and 50% is 0.5. To find that last column, we multiply across. So 0.8x. And then we have 16 times 0.1 gives me 1.6. And then we have 0.5 times x plus 16. The way we find mixture problems is to always add that last column. So we'll have 0.8x plus 1.6 equals 0.5 times x plus 16. I will let you go ahead and finish solving that.